Hi, I'm Darshana Sharma, and here's my lab report on Lab 3 circuits. So the purpose of this lab was to use principles of energy and current conservation and to predict the behavior of series and parallel circuits with resistors. We use multimeters to measure the actual value of conventional current and potential differences in the circuit. And a preview of my results is that I get RC equals 5.85 seconds, and I successfully predict circuit behavior using Ohm's law, node rule, and loop rule. So some fundamental principles used are conservation of energy and charge, which says that the total energy and charge in an isolated system cannot be created or destroyed. I use Kirchhoff's law, which is loop rule, and node rule, which is that the voltage in a loop, the change of voltage in a loop will all equal zero, and that the current going into a node equals the current going out of a node. I also use Ohm's law, which is voltage equals current times resistance, and I also use the concepts of resistors and capacitors in series and parallel, which tells me that in series I can just add the resistors straight up, and that in a parallel, I have to add one over the resistor value. I also use concepts of steady state circuit and capacitance. So the my first observed model is using the circuit kits provided in lab, which is two 1.5-volt batteries, alligator clips, multimeters, light bulbs, and resistors. And for my model two, I use a FET simulation of an ideal model. My assumptions are that Y resistance and ammeter resistance are both negligible, and that the EMF equals the change in voltage of capacitor plus change in voltage of resistor. And my system is the circuit, and the surrounding is everything else. So for part one, we created a series circuit with two 1.5-volt batteries, two resistors that are 47 and 100 ohms, and two ammeters. My predictions are that node rule tells me that I1 will be equal to I2 as the current is same going in and out of a node. My resistance is in series, so I can just add them up, which is 147 ohms. And rearranging Ohm's law, I get 0.020 amps. So my recorded reading is that when I get 0.015 amps, and when connected is reverse, my ammeter reads negative 0.015 amps. And when I replace the ammeter with the voltmeter, I get V equals 3 and I equals 0. And my circuit is open, so current cannot flow. And below is an image of my group circuit. So again, for part one, I calculate the voltage, or I measure the voltage in 8 different points along the circuit, and the sum I get when adding them up is 0.3 volts, and the sum should theoretically be zero because of the loop rule. However, my value is very small and it's close to zero, so this discrepancy can be due to issue with the batteries or voltmeter. Additionally, I measure the currents, and I get I1 and I2 both equal 0.015 amps, which is similar to my calculated value 0.020 amps, and this tells me that node rule is true because I1 does equal I2, and the ammeter reading doesn't change as voltmeter has high resistance, so the path of current is unchanged, as no current flows through it. And in my graph below, you can see that when potential increases, I have a positive slope. When a resistor is introduced, I have a negative slope, and I have no slope over wires because of negligible resistance. For part one, here are my calculated resistant values for 47 ohms, 100 ohms, resistance through the wire, and resistance to the ammeter. So for 47 ohms, I get 46.67 ohms. For 100 ohms, I get 140 ohms. And for both resistance through the wire and ammeter, there's no voltage flowing through these areas, so I get 0 ohms for both. My voltmeter connected across the 100 ohms resistor in series is 2.1 volts. And my ammeter in parallel with the 100 ohms resistor is 0.571 amps. So this means the current increases, and there's less current going through the 100 ohm resistor because it splits the node. So an ammeter has 0 ohms of resistance, so effective resistance of this part of the circuit decreases. So for part two, we have two 1.5-volt batteries, one F capacitor, and two light bulbs at 10 and 20 ohms. And what we're doing is looking at the difference between the discharge and charge time between the two different resistance values. So as you can see here, my discharge time and charge time for the 10 ohm batteries are a lot smaller than my discharge and charge time for my 20 ohm battery. This can be because a 20 ohm battery provides more resistance, so it takes a longer time for the charges to flow through and slowly discharge the bulb. And my observations for charging and discharging the capacitor are the same, that after the initial connection, the bulb is bright and dims until no light is emitted, and that the current starts at maximum and decreases zero. Additionally, this decrease is exponential, so it goes slower the longer it takes. So for part three, I used a FET to calculate RC, and I used the formula natural log of delta V over delta V naught is equal to negative T over RC. So first, I created the circuit with 9-volt battery, 0.2 F capacitor, and 30 ohms, and I calculate how long it takes to discharge in 20 seconds. And I get my experimental, and I graph it here to get my RC value. So I get that my experimental RC is 5.85 seconds, my theoretical RC is 6 seconds, and my experimental error is 2.5 seconds. So using the slope from my previous graph, which is negative 0.171, I set that equal to negative 1 over RC, and I get RC equals negative 1 over negative 0.171, which gives me 5.85 seconds. My theoretical RC should be 6 seconds, which is just ohms times the capacitor, which is 30 times 0.2, which is 6. And my experimental error I get from both these values is 2.5%. So there are similars, and the model is imperfect because of errors with multimeter and batteries. The actual model, however, my FET data it can probably be more accurate as it considers an ideal model and does not have like any failing multimeters or anything like that. Potential sources of errors could be inaccurate multimeter values received as they weren't working too well, depleted battery used in circuit as they were being used across many different labs, and human error when precisely collecting time and voltage data, especially in part three. So if I charge a capacitor without a resistor, my ideal model would predict that the capacitor would reach full charge instantly. This wouldn't happen in real life as wires provide resistance. And the measure time is different from the addictive time as the wires in circuit provide resistance and wouldn't charge instantly.